Good afternoon. We are Robotic Mining of Astronomic Surfaces. I'm Megan Brown.
I'm Hope Dormer.
I'm Nick Isley.
I'm Oren Kigner.
And I'm Rachel Straub.
So just to give some background on what we are going to be doing today, first we're going to introduce the concept of robotic mining in general, and then move on to our objective as a group in particular in this field. Then we're going to describe how we came to the decision of which astronomic surface we're going to mine, what robotic prototypes we wanted to build to test for their components, what those tests actually were, and what we concluded from those tests.
So in modern day society, luxuries such as electronics, medical devices, and jewelry are in very high demand. Unfortunately, Earth's limited supply of natural resources is simply unable to meet this demand. So in order to fuel these growing markets, it is necessary that we turn to another source for these resources, and that source is outer space. Planets and moons of our solar system are rich with elements that we can access through robots. And 3 large organizations are already launching the world into an era of astronomical mining. NASA is in the process of introducing its asteroid redirect mission, in which they plan on redirecting a portion of an asteroid into an orbit about the moon and then mining it for metals. Deep Space Industries predicts that entire markets will emerge based on astronomical resources. And planetary resources suggest that goods that are mined in space can either be brought back to Earth or used to fuel further space travel by creating rocket fuel or creating habitable environments on other planets. However, there are several factors that may inhibit robotic mining on astronomical surfaces, such as extremely cratered surfaces and extreme temperature changes.
Our main objective was to design a robot capable of mining an astronomic surface. So first we chose an extraterrestrial body based on factors such as environment and travel time. Then we built Lego robot models with features including claws and treads to see which would be most successful for navigating Titan and harvesting the chosen resource. After running tests, we gathered the data, and then we combined successful features into a final design. Once we had the final model, we recreated it through a computer-aided design program and stress tested it with different materials.
So our first major decision as a group was deciding which astronomical surface we wanted to mine. So we did this by researching 23 extraterrestrial bodies and dividing our research into pros, cons, and unique factors. Once this concluded, we created 5 weighted categories: environment, resource significance, background knowledge, travel, and public appeal. We then ranked each body individually over the 5 weighted categories and isolated the top 10. Group members were then given 10 points each to distribute to their personal discretion among the bodies. Saturn's moon Titan ultimately came out with the most points, largely due to its methane lakes, high gravity, and extensive background knowledge.
After choosing Titan as the astronomic surface to mine, we decided to conduct extensive research. Titan, one of Saturn's moons, is unique because it is one of the few moons to have an atmosphere. In addition, it has 1/7 the gravitational acceleration of Earth at 1.4 meters per second squared. Its average surface temperature is negative 178 degrees Celsius. Titan has a methane cycle, analogous to the water cycle on Earth, but it rains quite infrequently, only precipitating once per decade. The methane that is cycled through accumulates in a number of seas and lakes across Titan. Most of the methane bodies are concentrated near the North Pole. The surface of Titan is rocky and rugged, but below is a layer of soft sand. Due to the presence of an atmosphere, Titan's surface is relatively undisturbed by space debris. All of these contributing factors had to be taken into account when designing the robot.
Once we decided which astronomic surface we were going to mine, we had to choose 6 robotic prototypes we wanted to build. We chose these robots based on whether we felt they were capable of mining liquid methane on Titan. When choosing the robots, we took into account their maneuverability methods and whether or not they had a resource collection device. The 6 robots we decided on had varying designs. Their maneuverability methods varied from large and small wheels to treads, 2 walked and 1 even slithered, and 2 had resource collection devices. 1 had a claw and another had a lifting device. So we were curious to see how these various designs fared in our tests.
So of course, if we're designing a robot to mine on Titan, we want to make sure that the robot is capable of navigating on Titan's surface quickly. So in order to determine which robot is fastest, we designed 2 speed tests: the terrain surface speed test and the flat surface speed test. The single difference between these 2 tests is that the flat surface speed test took place indoors on a flat surface, and the terrain surface speed test took place outdoors on the uneven soil, which was meant to mimic Titan's surface. And both of these tests required that the robot travel in a straight line for a distance of 5 feet, and we timed the robots as they performed 3 trials for each test.
This video shows the Eve Meg model on the flat speed test. The positioning of its wheels allowed it to complete the test without turning, and of all the robots, it had the fastest time of 5.5 seconds. The next video shows the same model on the terrain test. Note that it only took 1/10 of a second longer on average to complete this test than it did on the flat speed test. Also, it did not get stuck or have balancing issues, showing that the wheels allowed it to move quickly and with low friction.
For the maneuverability test, we set up 3 cups and spaced each marker 1.5 feet apart. Each robot was set up a foot behind the first cup. We timed how long it took each robot to maneuver in and out of the cups and measured the displacement of each marker. The resource collection test was administered to the models Bobby and Gripper because they both had claw structures. We placed packing peanuts in a cup to simulate lightweight methane, and then we repeated the speed, terrain, and maneuverability test and accounted for the number of peanuts that fell out of the cup.
So here you see a video of the Reptar model performing the maneuverability test. The Reptar model had the fastest time for this test with an average of 7.5 seconds, and this was due to its flexible shape and ability to navigate the sharp turns of the course. And here is Gripper performing the resource collection test. The Gripper model had the fastest time, which was an average of 18.2 seconds, and also dropped an average of 0 packing peanuts in the process.
The 2 main features we decided to include in our final design were Eve Meg's wheels and the Gripper's claw. Eve Meg came in first in the flat speed and terrain test. It was also second in maneuverability to Reptar, which is a snake-like model. As for Gripper, it completed the resource collection test faster than the robot that used a lifting mechanism.
Now that we had decided on the major components of our robot, we needed to decide what materials they would be made out of in order so that they are as effective as possible. Because you're dealing with such a hostile environment on Titan, even to be considered, any material would have to be light, strong, extremely durable under extreme temperatures. Remember that the surface temperature of Titan is negative 178 degrees Celsius. Also, it would have to be relatively non-reactive because of the chemicals in Titan's atmosphere. We did our research and decided that we wanted to test 4 materials: titanium, aluminum, stainless steel, and carbon fiber. In order to actually test these materials, we created computer-aided design models of both components, and we also created a stress test for them that simulated conditions on Titan. For instance, we entered the gravitational acceleration of 1.4 meters per second squared. We entered the atmospheric pressure of Titan. In the case of the claw, we loaded 100 newtons on the end of it to simulate any load it would have to carry. We ran the simulation, switching out materials each time we ran it for both components, and analyzed it based on 2 different types of stress tests. The von Mises stress test, which is essentially finding the weakest and strongest points in a structure, and displacement, which is basically just how much something will bend when you put a force on it. After analyzing our data from these tests, we decided that carbon fiber would be the best material for the claw and titanium for the wheels.
So in order for the robot to be able to efficiently, in order for the robot to be able to locate the methane, it is necessary that we include some advanced features. So we will be incorporating 3 sensors into the design of the robot. The first is an inertial measurement unit, which consists of an accelerometer, which measures acceleration, and a gyroscope, which measures speed while turning. And for location purposes, we will be including star trackers. Star trackers allow the robot to take a picture of the sky and then compare that picture to a database in order to determine its location. And finally, we will be including a synthetic aperture radar and X-ray fluorescence spectrometer. These 2 work as a team to find the methane. So the synthetic aperture radar first detects a liquid by sensing refraction, and then the X-ray fluorescence spectrometer is then able to tell if that liquid is in fact methane. So once the methane is located, it will be mined using a centrifugal pump. And a centrifugal pump is essentially just a vacuum that pumps the methane into the robot. And to power the entire robot, we'll be using 1 primary power system and 2 backups. The primary power system is a methane engine, which just uses methane that has been mined to power the robot. The secondary power system uses heat released during radioactive decay to power the robot. And the third is solar cells, which is not very ideal due to Titan's distance from the sun and thick atmosphere.
One improvement we would have liked to have made would have been to administer the resource collection test with liquid, but we were afraid of damaging the robot. If we had access to sensor technology, we will create a test to determine the effectiveness of each sensor. In addition, if we did not have the time constraint of 4 weeks, we will design the entire robot instead of only key features.
So in conclusion, we created a conceptual model of a robot that has a carbon fiber claw and titanium wheels. We also decided on the appropriate sensors, resource collection systems, and power systems. On a more personal note, we hope that in a few years, this will not just be a theory, but will be, robots like this will be put into practical use throughout the solar system.
So we have some people we want to thank for making this all possible. First and foremost, we want to thank our amazing mentor, Nicholas Ferrero. We cannot be more grateful for his knowledge and guidance throughout this entire project. We also want to thank Dr. Eileen Rosen and Dean John Patrick Antoine for giving us the incredible opportunity of participating in GSET this summer. And lastly, we want to thank the Governor's School of Engineering and Technology and all of its sponsors for allowing us to enrich our understanding of engineering. These are our references. So thank you so much. Do you have any questions? Any questions? Yes.
When you listed your decision criteria for which surface to mine, one of that was public interest.
Yes.
What was the driver behind that?
Well, we didn't exactly want to choose a surface that the public didn't know about so that they wouldn't exactly not support the mission. So in order to have the public back it up and think, you know, we can go into space, we can mine extraterrestrial surfaces, we wanted to choose a planet or a moon. In this case, we chose the moon Titan that people would be excited about. Yes.
What made you choose methane as the element to mine?
Well, when we were choosing the planets, each planet had their own resource that we could mine. So Titan had really large methane lakes, and so we felt that these could be used as fuel to propel us further into space. So the methane was, we didn't originally set our minds to choosing methane, it was just the resource that was abundant on the body we chose.
Yeah.
Yes.
Titan has like a rocky sort of surface, like most things do in outer space, and we searched around the area of where we were doing our project to find a surface that most matched that, and we found like a patch of dirt that we thought would work well.
Yeah, we know it's dirt, but like,
You can't go to space.
Any other questions? Yes.
So methane is a liquid at that temperature, or is it a gas?
It's a- At the temperature of negative 178 degrees, it's a liquid.
So you're going to put a pump to collect your things instead of like a claw, right?
Yes.
The
Yeah,
claw is more for like a canister of it.
What?
The claw is designed like if you had a canister of the liquid.
Okay.
Yeah, so first it's like pumped into the robot, and then it goes into canisters, and the robot will then carry the canisters to a location.
Okay. Good.
Yes.
Do you know how far away Titan is and how long it will take to get there?
That was not a big concern for us. It was not within the scope of our research.
I think it's 2 years, but I'm not sure.
Any other questions? Well, thank you so much.